Okay, so finally we are going to introduce the last lecture for CUDA programming, and we will talk about performance optimization, specifically on the memory management, because we keep saying that the data access on memory usually is the bottleneck for GPU programming, right? So all the optimization technique we introduce in this lecture is about the memory access. Okay, and here we can see that why memory is the bottleneck by looking at some of the statistics or performance numbers, right? And by analyzing those numbers, you can easily see that why communication or the memory data transfer is the bottleneck on GPU. Okay, so you can look at it in two different ways. One is from the flops, right? From the performance metrics of flops. And so you can calculate the ideal flops on a GPU according to its hardware spec, right? Such as how many string processor does it have, how many cores on each string processor, and what's the computing capability, right? From the core. Then you can calculate the ideal number of flops for that GPU device. Okay, and here we use Kepler as example. And so for this particular GPU device, according to the spec, you can expect to reach almost 4,000 gigaflops, which is 4 teraflops. Okay. On the other hand, for the memory access, specifically, usually we look at the memory bandwidth from the GPU core to the device memory or the global memory within the GPU card. Okay, and for Kepler, right, you can see according to the spec, it's about 250 gigabytes per second. Okay, so imagine, right, for each flops, right, it's an operation on the floating point. So a floating point number actually require 4 bytes, right? So to just operate on a single flops at on the 4 teraflops speed, then that's almost 64 times more than the bandwidth you have to access those data from the device memory. Okay, so you can see the amount of data you need to consume needs to be a lot more in order to capture with the amount of data you can consume at your computing core or on your GPU core. Okay, so it's a very theoretical analysis, right? Like a theoretical analysis on the bound, okay, on the performance, okay, and it's a 6 times difference. Okay, so that means computation needs to be actually the data transfer, right? The data transfer performance needs to be improved by 60 times in order to catch up with the computing performance. Okay, and another easier way to look at this performance differences is from the computing cycle you need, right, for each individual say data access and each instruction operation. Okay, so you can see again from the spec, you can see for instruction maybe takes about 1 to 4 cycles, computing cycles. While if you encounter a memory store, then it will require maybe 400 to 800 cycles to access the global memory or the device memory. Okay? Even if you can access the data on the shared memory, it might take up to 20 cycles, right? It's still 5 times more than process instruction. Okay, so the ratio could grow even further if you look at from the computing cycle point of view. Okay, all right. So no matter how you look at it, right, basically it's very likely your computation on the GPU is bounded by the memory access time. Okay, so that's why it's so important to reduce the memory time, right? Or reduce amount of memory access. Okay. So of course, there are some already, from the hardware and software point of view, people are already trying very hard to resolve this bottleneck. So that's why you can see that for the newer generation or newer architecture, GPU architecture, they try to provide better bandwidth or shorter memory access latency, or install more cache or register to help you reduce the memory access time. Okay? So that's from the hardware point of view, and that's why people, one of the reason people try to buy those newer version of GPU is because to get better memory access time. Not really about the computing capability nowadays. Okay. And however, that's hardware that's very costly, right? You have to always try to, you can only get a better performance by buying the new device, new hardware. Okay, so as a programmer, we certainly can try to resolve this issue by just simply rewrite our code, right? If we know how to optimize the performance. Okay. So we can do that by basically two ways. One is minimize the memory access, right? The other is to try to reuse the data. So we could store those reused data in shared memory or even in register. So we don't need to access the slower memory device. Okay. And so as we will show at the end of this lecture, you could actually improve your performance by, say, more than 100 times on GPU just by rewriting your code. So that's why people usually say that it's not hard to port your program on GPU. You could even do that by compiler, like tool like OpenMP, OpenACC, but it's very hard. It's very challenging to optimize your performance on GPU. That's why still need expert to do that, and it's still a talent that's very demanding from industry. Okay, so for this course, of course, you might not reach that level yet because it requires lots of experience and skills. But at least you know the basic concept, and you know some of the basic techniques, which should be enough to at least ensure your performance is not is reasonable on a GPU. Okay. All right. So as we know, the memory architecture or the memory hierarchy on GPU is quite complicated, right? You have several layers. So on each layer, you can optimize the performance with the different scales, because every layer of memory, they might provided by different hardware architecture or different memory devices. Okay, so the way to improve the performance may be different because they are all different memory chips or memory architecture inside. Okay, so you can see that we will introduce those optimization layer by layer from the host memory to the global memory and then to the shared memory. Okay. And the outer layer, right, like the layer that closer to the host, usually is the slowest one, right? So that should be the first performance bottleneck you try to resolve. So you usually work on your optimization layer by layer, right? You try to resolve the bottleneck first, the current performance bottleneck first, and then you might encounter the bottleneck from the next layer, and then you try to resolve that as well until you try to optimize the performance on every layers. Okay. All right, so we will talk about the host memory first, and then move toward the inside the GPU. Okay. Okay, so there are a couple of general optimization technique that could apply on the host memory. Host memory means here means the memory transfer overhead or time from the host memory to the device memory. Okay, so how can we, right? Because originally the data should be all stored on the host memory, and so how could we provide, how we could access or move that data content from the host memory to the GPU for our computing. Okay, so the first strategy is called the page locked data transfer. Okay, so which means we will pin the memory on the host. Okay, so that the GPU, when he try to transfer the data, he can bypass the operating system, use the physical memory address to access the data for data transfer. Okay, this is the same technique, right? We actually mentioned before for a string or for asynchronous memory copy, right? All those techniques require the require the data on the host memory to be pinned or to be locked, so that the address can the physical address can given to the GPU, and GPU can directly use that physical address to access the memory. That's why it can bypass the operating system and supposedly can reduce your data transfer time or data access time, right? Okay. So we have seen this technique combined with other memory copy and other API before. Okay, so this is our first technique. Okay. However, there's a drawback for this technique. That is, if you pin too much memory on the host side, then you will leave fewer amount of or less amount of memory, physical memory, for the operating system and other processes on the host, right? So it might reduce the overall system performance on the host side. Okay, and remember we are talking about heterogeneous computing. We are not just talking about GPU computing. So sometimes if you you reduce the performance on the host side, could also cause performance degradation of the overall system or overall application performance. Okay, right. So usually we will not try to pin too much host memory. Okay, all right. The second strategy is also very general, and we have talked about it before, right? That is try to overlap the CPU time and the GPU time, since they are two independent devices. Okay, and we could do that because of most of the API are asynchronous. So potentially we can overlap those computation time together, right? Okay, so you can see this is a example. We can just look at the illustration on the right side, the figure on the right side. Okay, so say we have some kernel launch execution, and we have some CPU functions. Okay, and the kernel launch command actually is they are asynchronous, but the cooldown copy is a synchronous code. So that's why if you write the you call the CPU function after the cooldown copy, then the CPU side actually cannot do anything while the GPU is running your kernel. So if we want to, if there's no data dependency between the CPU function and the GPU kernels, then supposedly what we could do is to move this CPU function to this hop over here, right? To fill up this time, so you can allow CPU and GPU to compute at the same time. Okay. So how could you do that? Several ways to do that, right? First strategy is first solution. It could be you simply move your CPU method to in front of the cooldown copy, right? So in this way, after the host launch those two kernels on the GPU, the CPU can immediately execute or run the CPU methods, while the GPU is running the kernel functions. Okay. All right. But however, this way you could only overlap the computation time. You cannot overlap the CPU time with the data transfer time, the CUDA main copy time. Okay. So another way is to use the asynchronous memory copy. Okay. So by doing this, then even the data transfer time can be overlapped with the CPU time. Okay. And the way to do that is, of course, to call the CUDA main copy async function. Okay? And in order to do that, the host, right, the host memory needs to be pinged. Okay? Because again, the reason the memory copy can be done by just GPU is because the GPU already obtained the physical address on the host memory. Okay. So you need to pin the host memory to ensure the physical address can be obtained for the GPU. Okay, all right. So you have to when you allocate the host, we have told that before, right? When you allocate the you need to use a different API to allocate the host memory, and make sure you enable the ping configuration in your allocation API. So the OS knows the memory is pinged or is locked. Then you can pass that host pointer to this async memory copy code. Okay. And another thing you need to pay attention is it's according to the API. Okay, you also need to have the last argument to indicate which string you are. Okay, and we will explain what is string in the next page. Okay, and so by default, we set all the CUDA event is sent it to the string 0. Okay, so that's why by default you should just put the 0 over here. Okay, unless your CUDA event is applied to a different string you created, then you need to put the string ID for that string in this API code. Okay. All right. So what is a string? Okay. We briefly mentioned it before, but we formally introduce it now. Okay. So a string, you can think it as a cube, right? It's a task cube for the GPU. So all the CUDA event you created through those API code, like kernel launch command, they will all send it to a task queue, a string. Okay, and the GPU will pull those tasks out from the string, from the queue, and try to execute them on the GPU one by one. Okay, so all the tasks actually they are executed on the GPU in a serialized version, in a serialized manner. Okay, although they are sent from the host in an asynchronous code, but they are actually executed in a serialized manner on GPU. Okay, as long as they are they are sent it to the same string, because a string is, you can think it as a FIFO queue. Okay, so this is how GPU and CPU work asynchronously through this string, or sometimes we call it as a working queue. Yeah, a FIFO queue. Okay. All right. So so the design of the string is allow the user to create more strings on a GPU, so that the programmer can send those CUDA event or GPU tasks to different string, and different string they can execute it concurrently. Okay, so in other words, if you want to execute two kernels simultaneously on a GPU, then you could do that by creating two strings, okay, and send the kernel to different string, and then they will actually be executed on GPU concurrently. Okay, all right. So you can see the purpose of a string is to increase the parallelism, right, on GPU. Okay? And so what's the application for this technique? One of the application is pipeline computing, right? So I think all of you know what is a pipeline, and if you look at how the workflow, right, of a kernel execution, then you will see a kernel execution usually consists of 3 stages, right? The first stage is to move the data you need from host to the device memory, to GPU. The second stage is to execute your kernel on GPU. And the third stage is to move your data from the device memory back to the host memory. Okay. So any CUDA execution normally consists of those 3 stages, right? And those 3 stages actually perform on different hardware component, right? The host to device and device to host, they are performing on the memory bandwidth, right? And actually, the memory bandwidth between host and the GPU are bidirectional. Okay, so they are actually occupy different memory network capacity. Okay, 2 different network links essentially. Okay, and the kernel execution certainly separate from data movement, right? So you are utilize the computing power of the GPU instead of the data transfer bandwidth. Okay, so all those 3 stages, they are performing on different hardware component, which means they can actually utilize their resources at the same time, right, in parallel. Okay, just like our CPU pipeline strategy. Okay, so so the idea is like the figure below, right? Say if we have 3 kernels that needs to be executed, or originally say we have just a single kernel to execute, and we have lots of data, right, that needs to be processed by the kernel. So you require a very long data transfer time, right, as shown above over here. Okay, so if your kernel execution on those data, right, can be partitioned, right, into several phases, right? For example, 3 phases as shown over here. The first kernel try to process the first 1/3 half of the data, and then the second kernel try to process the second partition, right? And the third kernel try to process the last partition. Okay, then we can parallelize, right? Parallelize those computation and data transfer as the pipeline shown over here, right? So we can first transfer the first partition to the GPU, and after we pass the data to the GPU, then in the second phase, in the second stage, we can let the GPU to process the data while we sending the second batch of the data to the GPU, right? And then in the next phase, the first batch of data is completed, so we can transfer it from the device to host, while the GPU is executing the second kernel to process the second batch of data. And then we can send the partition, the data of the third partition, right, to the GPU. All those things can do it at the same time. Okay, so that we can fully utilize, we can overlap the data transfer time with the GPU computing time. Okay, all right. This is string. Okay, so string basically, we usually use it for 2 purposes. First is to implement the pipeline as we shown over here, in order to overlap the data transfer time with the GPU computing time. Okay, the second reason is we are not showing here, but it's very simple to understand. That is try to launch multiple kernels on the GPU at the same time, in order to utilize more computing power or computing capability on the GPU, right? Because maybe your kernel is not large enough to utilize all the GPU core. And so if you have some multiple kernels, they don't have dependency to each other, then you could create string to launch all of those kernels to the GPU at the same time in order to fully utilize your GPU. Okay. All right. So that is string. Okay. However, you need to note that especially if it's for the pipeline case. Okay. Usually we don't create too many strings, meaning that we usually don't try to partition the data to too many partitions. The reason is because, of course, if you create string, there's some overhead associated with it, right? So there's always some overhead to pay. Okay. And secondly, because unfortunately, the data transfer time and the computing time usually they are not the same. And as we know, for pipeline, if you want it to be efficient, then the time for each stage should be similar, right? But it's very hard to do it on GPU in normal case, right? Usually, the data transfer time will still be much longer than the kernel execution time. So by doing this pipeline techniques, the amount of time you could save usually is still quite limited. Okay, but so for some cases it might be helpful. Okay, and so this is the optimization you should know and you should keep in mind and try to apply that if you think it will help on your use case. Okay, all right, and so we introduced the concept. So how can we implement it? Okay, it's quite easy to implement it. The way to create a string is, as you can see over here, there is a predefined data type for string called the CUDA string type. Okay, and after you create this variable, you have to initiate this object. Okay, so you have to call the CUDA string create. Okay, on this string object. Okay, and only after that you are allowed to use the string ID. Okay, to launch your event, any CUDA event to that string for processing on GPU. Okay, and if you don't use it anymore, you can destroy the string, and you should destroy it in order to release some of the GPU resources. Okay. All right, so this is how you could use it. And if you want to use it with, for this pipeline, right, case, then you should co-work with the asynchronous memory copy, right? Because as you can see over here, we need to keep sending memory to GPU without waiting the completion of your kernel execution. Okay, so you don't want to block your kernel submission by a synchronous memory copy code. So this use case is implemented with string and asynchronous memory copy. Okay. All right. So we have a complete pseudocode for you as a reference. Okay. So you can see over here, we create two string. And we try to do the memory copy and kernel launch on those two strings independently and concurrently. Okay? And so to do that, our memory copy should be asynchronous memory copy. Okay, and this is what we mentioned before. If you want to use memory asynchronous memory copy, when you allocate the host memory, you need to allocate it with pinned memory. Okay. So you need to use some special API like CUDA malloc host to allocate the host memory instead of just the regular malloc API. Okay, and all those things you can see, all those API here are asynchronous code. So that means the GPU will on those two strings can be processed concurrently at the same time. Okay. All right, and especially for pipeline, right? in this case, we simply try to have multiple streams work concurrently. But for the pipeline, you need to further synchronize the stage, right, across the string, right? For example, over here, you want to make sure your memory copy is complete before you can launch the kernel on GPU, right? So there's some dependency, right, across those steps. Okay. So how could you do that? You can use the CUDA string synchronized code. Okay, so this will similar to the CUDA event we introduced before, but at that time we haven't introduced string yet. And here you can see we can extend that to synchronize your event on a specific string. Okay, so this usually can, if you create string, then you want to synchronize the string, then you need to use the string-based synchronization API. Okay, and how to use it is very similar to the CUDA event record we introduced before. Instead, that the only difference here, you can see if we schedule an event record, we will specify which string ID we schedule this event on, right? And when we try to block the when we try to synchronize the computation, here we can synchronize for a particular string to block the event on some string according to some event. Okay. All right. So let's just see the example to understand it more easily, right? So like the pipeline example we showed before, right? What happened is, as we said, the kernel, right, for string 2, for example, it needs to be blocked, okay, until the memory copy event on the first string is finished. So the way to do this is, of course, first of all, we will insert an event record API, right? And we will insert it right after the synchronization point. We want to create it. And so this point should be after the host to device memory copy API, right? Which is this one, right? And it's happened on string 1, okay? And this, because this event is scheduled on string 1, so the event record, we need to also schedule it on string 1, okay? If it's on string 2, then you will be record after whatever the previous event on string 2, not string 1, okay? But here we want to wait the event on string 1, so we need to insert this event record on string 1 as well. Okay. However, this event can be, can block any string, any string on the event on any other strings. Okay, so we call this CUDA string wait event on string 2. So that means we insert a synchronous blocking code on string 2, right? And this blocking event, right, or this blocking code will not return until this event is record. Okay, and this event could be record on any other string, right? In this particular case, it is an event, record on string 1, but it will block the event on string 2. Okay, so that's why we can synchronize the event across strings. Okay, all right. So yeah, so the pseudocode over here will create the result showing over here. Okay, and so you just follow the definition of the API, and then depends on how you want to create your synchronization point, and then you should be able to do that. Okay, so of course it will be a bit more complicated, but if you think through it, then make the code properly, then you can see the API allows you to synchronize the string in any way you want. Okay. All right. So so you can follow this example, to realize the pipeline behavior we talked about before. Okay. Okay. So that's the optimization for the host. Okay. So you can see that we can this is we try to reduce the time, right, or hide the memory transfer time from the host memory to the device memory. Okay. So we move on to the next level. The next level is for global memory, okay, or local memory, because we said that both global memory and local memory, they are actually both located on the off-chip memory. So off-chip memory have the same, they are actually from the same memory hardware architecture, hardware component. So of course they have the same, same behavior for memory access. Okay, so both of them, as long as it's on the off-chip memory, then the optimization you want to use is called the closest memory access, and this is optimization you're going to exercise or require to do in your lab tonight. Okay, so let's introduce what is closest memory. Okay. And before that, we just have a quick look, right? Remind you, right? What's a local memory and what's a global memory? Okay. So actually, they are both on the off-chip memory, as we said. The only difference is their access scope is different, right? The local memory store the data that can only be accessed by a single thread. That's why it's called the local memory. On the other hand, the global memory is why we said the device memory. So it can be accessed by any threads on GPU. Okay, but essentially they are stored on the same memory chip. So that's why they have the same behavior. Okay, but for local memory, additionally for optimization, it will be cached because it doesn't have any data consistency issue because it's a private data, right? It's a non-shared memory content, so it can easily be cached in order to provide faster access time, and this is done by the hardware. So so it's an optimization built inside the GPU. Okay. So what is closed memory access? Okay, so closed memory access is essentially the same as collective I/O we have told from the MPI library, if you can still remember. The idea is that if you have many small memory access, right, we can collect them together into a single big chunk of data access. And so that will usually improve the memory access time because you can reduce the amount of memory access request, and you can reduce advertise some of the constant latency delay, right? So usually for I/O device, if you know the data transfer size, the larger the better. Okay, so closest memory is such technique applied on the off-chip memory or on the device memory. Okay, that will try to automatically collect your memory access together and issue them in a single request and handled by a single memory access request to the memory. Okay. All right. So as you can see over here, we have several arrows pointed to the memory chip over here. Each arrow indicates a memory access from a single thread. And you can see that noted that the thread we're talking about here should be from the same WAP. Okay, if it's not on the same WAP, they are not even executed in parallel physically. So of course, it will not be able to take advantage the closest memory access optimization. Okay, so only the threads in the WAP, they are guaranteed to access data at the same time. Then we have an opportunity to collect them together and read it out more efficiently. Okay, so that's why you can imagine if we want to take advantage closest memory, then you should ensure the memory access from the threads of a WAP should be continuously. Okay, so they can, if there's a continue and they access in the near range, right, near location, then you can read them out collectively in a single request. Okay. The second thing you need to notice is that the closest memory access will also be applied on the cache, okay, especially for local memory. So for cache, usually they have the cache line. So cache line means some units, for example, 128 bytes for the L1 cache, and probably just 16 bytes for the L2 cache, which means the data will be read out or written access by this unit. Okay, so if your access is not aligned to the cache line, then it may result reading more data, like showing below. Okay, so originally, say you only need to read 128 bytes. If you align to the cache line boundary, then you will read exactly the same size. But if you are close to cache line, then the amount of data you need to read out is twice amount of the data. Okay, so that of course will also prolong your data access time, right? Increase your data transfer time. Okay, all right. So usually you want them to be read out collectively and aligned to the cache line. Okay, so the same thing for L2, as we mentioned. In this example, if the cache line is 32 bytes, then you should also align to the 32 bytes boundary. Okay. The reason usually we have a smaller cache line for a slower level of cache, because the lower cache is slower. So you don't want to, the effect or the overhead for reading out more data is more significant. So that's why usually for cache, the design of the cache, they use a smaller unit for the lower level cache. Okay. But anyway, for you, it's quite simple. Basically, you always try to read data or write data from the offset 0, right? So that makes sure no matter what the size of the cache line, you can align the best you can. Okay. All right. So, however, if you try to read some data from the middle of your array or from your buffer, then you should be more attention, pay more attention on whether it's at least a factor of 2 location. Okay, so you have a better chance to align to the cache line. Okay. All right. So let's just look at an example to wrap up this this optimization. Okay. Why closest access important and how we can apply that in our code. We use this matrix transportation as example. Okay, so in this use case, in this example, what we try to do is to transpose a matrix, right, from the matrix we think at the right hand side to the left hand side. Okay, so we just transport by 90 degrees, right? Okay. And so if you write this code on your own in a naive way, you can do this by a single statement in the kernel function, right? The statement probably should be such as aij equal to aji, right? Or aij equal to bji if you want to read out from different position, right? To different memory buffer. Okay, so you only need the one line to move the data from say A array to B array and transport the matrix. Okay. However, in that implementation, if you look more carefully on the memory access pattern on your global memory or device memory, then you will find that when you try to read it in the row major, then you have to write it in the column major. Okay. Or if you want to read it in the color major, then you have to read it in the write it in the row major. Either way, they are different dimension. Okay, so what happened is for the matrix, when they get serialized on the physical memory, such as device memory or global memory, it's always in row major. Okay, so in this case, for example, if we read it out from the row in a row major way, then we can read it sequentially without any problem. So we can take advantage the closest memory access performance. Okay? However, when we try to write it Unfortunately, you will see that the color marked in green, we say this, you can imagine it as the threads within the WAP. Okay, so you can see they read at the same time and write it in the same time as well. Okay, and for when they write it, because it's a column major, not row major. So what happened is the thread inside a WAP, they will write it out in a stripe way, right? So it's a striping. You have a stripe across the element you write it on the device memory, and you will be far away from each other. Okay, so that means you cannot take advantage the closest memory access performance. Okay, so you can only have that optimized performance on read or on write, but you cannot have it on both. Okay, all right. So how can we have both, right? Achieve the better end of the two side. Okay, so what you could do is through shared memory. Okay, so why? First of all, that just keep in mind that for shared memory, it doesn't care it's row major or column major. It's more like it's more like a cache. So no matter how you read it, write it, you always can provide the consistent access performance, as long as you don't have a bank conflict. And we will introduce that later on. So for now, you just assuming no matter how you read or write the element from shared memory, they can have the same performance. Okay. So under that assumption, right, we can rewrite our code from just one statement in the kernel function to two statements. The first statement is to move the data from the global memory to the shared memory. Okay. And then the second statement is to move the data from the shared memory to the global memory. Okay. We need two statements because you can see that when we try to read it, we read it using the row major. Okay. But when we try to write it, we read it out from shared memory in the column major. Okay. So for the same thread, when he read and write, they are actually read and write on different elements in this example. So that's why you need to have two statements in your kernel function. Okay, because a thread who try to read an element will write another element from another thread. Okay, so that's why you need two statements. And as a matter of fact, we don't have the pseudocode here, but you also need a thread synchronous code between two statements, right? To make sure every threads move their data to the shared memory before they can move the data back to the global memory again. Okay. And why we need to change the reading order and the order for the first statement and the second statement. The reason is because, as you can see here, when we try to, after we do this change, right? When we try to read the data from the global memory, or when we try to write the data to the global memory, they are both row major, right? So row major means they can align to, they can become serialized access on the physical memory. Okay, so basically, we want to make sure whenever we try to access the global memory, it's accessed in the row major manner. Okay, so that's why we need a shared memory in between to change our memory access pattern in order to make sure they are always access the global memory in a row major way. Okay. All right. So okay, so you can see this implementation will actually introduce additional memory copy to the shared memory. But remember, shared memory access is way much faster than global memory access. That's about 10 to 100 times faster. So the time can essentially ignore over here. So all we need to make sure is to ensure the global memory access performance is optimized. Okay. So by doing this, we can ensure that. Okay. All right. So we are also running out of time. So in the next lecture, we'll continue to talk about the the tail algorithm, which is try to use the shared memory we introduced before to store the reuse data. And how we decide that the strategy in general is what we call the tail algorithm. Okay, and then we'll wrap up with the optimization on the shared memory. Okay, any questions?